Hey guys, in the previous video, we showed how you can use 3 single-phase transformers to create a 3-phase transformer bank. Connected in a delta-delta configuration, this transformer bank provides single-phase 120 volt and 240 volt power, as well as 3-phase 240 volt power. In this video, we're going to show how you can connect the same 3 transformers in a delta-wye configuration to produce single-phase 120 volt power and 3-phase 208 volt power. We'll then talk about what this type of transformer is used for. Let's get to work. Since we want to use the same 12,000 volt transformers we used in the last video, we'll need to connect them to the primary system in a delta configuration, the same way we did last time. We'll start by connecting the 2 short jumper wires. The jumper on the left and then the jumper on the right. Then we'll connect the long jumper wire, which completes the delta configuration. We'll add the A phase lead, the C phase lead, and finally the B phase lead. You can see the primary delta connection in this image. The 2 transformers on the left are connected with a short jumper wire. The 2 transformers on the right are connected with another short jumper wire. The 2 outer transformers are connected with a long jumper wire. This long jumper wire is connected to the A phase primary conductor with a lead wire. The connection is hidden behind the tank in the image. The short jumper wire on the left is connected to the B phase primary conductor. And finally, the jumper on the right is connected to the C phase conductor. Since we're here, let's look at some of this other stuff for a moment. The thing the transformer tanks are attached to is called a transformer mounting bracket. This particular bracket is designed to hold 3 transformer tanks. The insulator holding the long jumper wire is called a standoff insulator. This insulator, along with the very long insulator mounting pin, is meant to hold the long jumper wire away from the steel pole. The 3 small wires on the bottom of each of the 3 tanks are ground wires. They're attached to the steel pole to provide a protective path to ground for the steel tank itself. Now that we've completed the delta connection on the primary side of the transformer bank, let's move that aside and take a look at how the secondary side is going to be connected. Before we do, though, let's take a look at the secondary windings in this transformer for a moment. We already know the transformer produces a secondary voltage of 240 volts across the full secondary winding. The Y connection we're going to look at only utilizes the 120 volt potential between the center tap and one of the phase leads, using only 1/2 of the winding. To see how this works, we're going to look at just the right half of the secondary winding in transformer number 1. We'll add the same half of the secondary winding in transformer number 2. And then number 3. We're going to connect the center tap of each transformer with a long jumper wire and a lead wire. Shown on the right, this becomes our neutral. We'll then add the X phase lead to the left transformer. And shown on the right, this produces a 120 volt potential between the X phase and the neutral, since this connection is only utilizing half of the winding in the 240 volt transformer. We'll then connect the Y phase lead to the same position of the middle transformer, which creates another 120 volt potential to the neutral. Finally, we'll connect the Z phase lead the same way, creating another 120 volt potential to the neutral. If you remember from the previous video, the delta connection only provides single-phase 120 volt power across the windings of the middle transformer. This Y connection produces the same 120 volt power, but it does so across all three transformer windings. To determine the phase-to-phase voltage potential, say between Z phase and the X phase, we'll need to look at the phasor diagram. To determine the voltage potential between the Z phase and the X phase, we just need to use some simple geometry again. We know the phase to neutral potential is 120 volts. We also know this lower interior angle is 120 degrees. If we simplify this by just looking at this right triangle, we know the lower interior angle is now 60 degrees. The sine of this 60-degree angle is the value we're looking for divided by 120 volts. Rearranging the terms, we end up with 120 volts times the sine of 60 degrees, which equals 104 volts. And since this is 1/2 of the distance between Z and X, we now know the voltage potential to be 208 volts. So the phase-to-phase potential between the Z and X phases is 208 volts. The symmetry of this connection also shows us the potential between the Z and Y phases and the Y and X phases is all 208 volts. This is the three-phase power of this Y-connected transformer bank. The secondary Y connection can be seen here. The center tap of each of the three transformers are all connected together with two jumper wires. Along with this lead wire, this all becomes the neutral. The X phase lead wire is connected to the right side bushing of the transformer on the left. The Y phase lead wire is also connected to the right side bushing of the middle transformer. And the Z phase lead wire is connected to the right side bushing of the transformer on the right. These four conductors make up the three-phase, four-wire service connected to the customer's meter panel. The four conductors are attached to the customer's meter panel: X phase, Y phase, Z phase, and the neutral. Bus bars carry the power through the meter so the utility can monitor power consumption. Another set of four conductors carry the power to the distribution panel. Now, a Y-connected transformer bank can provide 120-volt power by using the X phase and the neutral, the Y phase and the neutral, and also the Z phase and the neutral. Because of the ability to utilize all three windings to produce single-phase 120-volt power, this type of transformer is very popular with office buildings. For example, in this three-story office building, the entire first floor can be energized using the X phase, the second floor with the Y phase, and the third floor with the Z phase. The three-phase 208-volt power can be routed to the roof to provide power to the air conditioning and the elevator motors. The ability to evenly utilize all three windings in the transformer to provide a lot of single-phase 120-volt power is the advantage that this type of transformer bank has when compared to the delta-connected bank we looked at in the previous video. For the same reason, the pad-mounted version of this transformer is also used a lot to provide power to apartment buildings, fast food restaurants, and has recently become very popular for electric vehicle charging stations. A couple quick things to mention before we conclude. The Y-connected 120 208-volt transformer bank is able to provide balanced 120-volt single-phase power across all three transformer windings. However, the three-phase power output is reduced from 240 volts to 208 volts. And finally, this is usually recognized by the utility as a three-phase 120 208-volt service. Thanks for watching.